So we'll follow up with the rest of chemistry with this last portion of chapter 2. I like the way this one's put, so we're going to kind of copy it with our essential question. And we'll do what are water's life-supporting properties. I have cleaned my monitor since then, so I can write these things just a little better. Property. Okay. Central question, what are water's life-supporting properties? Seems a fairly good question. So hydrogen bonds that we talked about at the end of the last lecture actually make liquid water cohesive. So we talked a tiny bit about hydrogen bonds, and we'll make sure that we follow through a little bit more when we spend more of the next class period together. But hydrogen bonds are what make water cohesive. So really it's just the tendency of molecules of the same kind to stick together. So I say cohesion is more of stick to self. That's the way I think of it. So stick to self. So cohesion is sticking to itself. Cohesion is much stronger in water than a lot of other liquids. So most plants depend upon cohesion to help transport water and nutrients from the roots to the leaves. This is also how you maybe get a Starbucks Frappuccino up a straw. It's the cohesive property of the water. Okay, so it also has the tendency of two kinds of molecules to stick together, so that's adhesion. So cohesion, stick to self, adhesion is stick to others. Or stick to other stuff. So we could say other stuff too. All right. Cohesion, so the stick to self, is related to surface tension, and it's a measure of how difficult it is to break the surface of a liquid. So hydrogen bonds give water a high surface tension, making it behave as if it were coated with an invisible film. So that's the thing, is it's actually difficult to break through water. So that's why we have some water striders that can stand on the water without breaking the surface. There are also these amazing lizards, they're called basilisks, the Jesus lizard. And so it's a little harder to break. So we have a good animation, and I'll make sure that it's available to you, but what happens is that we get water molecules and they can stick to themselves, so they stick themselves on the way up. But the thing is they also stick to the walls of the kind of the cell of these tubes and make their way out. So it's actually how water is able to transport from the roots all the way up to the plant, up to the leaves of the plant. And here's a little water strider. He's sitting on water, and it's got a high surface tension, so he's actually able to sit on top of it. All right, thermal energy. So the word thermal just means heat, so we're talking about some heat energy. So it's the energy associated with the random movement of atoms and molecules. So thermal energy is a transfer of a warmer to a cooler body, and that's defined as heat. Okay. Temperature measures the intensity of the heat. So temperature is just the way that we measure heat. And heat is really just the average speed of molecules in a body of matter. So something to think of since we're on water. So think about kind of how water flows. So it's moving quite a bit. It's got some energy. But then whenever you have, let's say, a pot and you're boiling water, well, then you get this really intense kind of movement of water. So as we increase the heat underneath it, I don't know, this is supposed to be like a little fire. Do a little fire there. As you increase the heat underneath this pot, it gives more intensity to the water, more movement. So that's really what we're talking about, is increased movement of those molecules. You'll get more of my doodles as we go along. All right, so heat must be absorbed to break hydrogen bonds. So there's hydrogen bonds between those water molecules, and so heat must be absorbed to break hydrogen bonds. Okay, so as we get hotter, as you get to kind of water vapor, you have kind of non-existent hydrogen bonds. So the little hydrogen bonds just don't really happen because we have enough heat, so those bonds are broken. So heat released is the other way of saying things cool. So it sort of cools when those bonds form. So actually ice cubes will have more sort of rigid hydrogen bonds. So to raise the temperature of water, hydrogen bonds between molecules must be broken before the molecules can then move faster. Okay. When warming up, water absorbs a large amount of heat, and when water cools, those molecules slow down, more hydrogen bonds form, and a considerable amount of heat is released. Okay, so that's a good way to look at it. Okay, good way to think about it. It can be hard to visualize though, so we'll try to get some animations and things to look at in the helpful materials on that one. If you have any questions or really just can't visualize it, let me know, but we should be able to at least look at some videos or see some visuals. We have to rely on a lot of other people's animations during these kinds of sections because it's hard to visualize and you can't just go look at it in nature. Alright, so Earth's giant water supply moderates temperatures, helping to keep temperatures within the limits that permit life. Water's resistance to temperature change, this is also kind of one of those key factors of water, also helps stabilize ocean temperatures, creating a favorable environment for marine life. So that's also, so this is good for us, as since we live near the coast, we recognize that a lot, is that you can be in places like the desert that get to -degrees at night, and then during the day they're super hot because it's completely landlocked. Whereas when we're here next to the ocean, our temperatures are relatively stable. Okay, this is a good one to know. So when a substance evaporates, the surface of that liquid will remain behind, will cool down. So this is a process of evaporative cooling. The cooling occurs because the molecules with the greatest energy leave the surface, and what's left over are kind of the coolest ones. So this is actually the idea behind sweating. If you're like me, I'm, you know, I got it from my dad. I'm a very heavy sweater, but I just say it's me efficiently cooling. So that's the evaporative cooling, is the more you sweat, the more it actually helps maintain body temperature and keep you cool. So that's an important body process for maintaining what we call the homeostasis. All right, so here's a guy sweating, and you can see because it's cold outside, you're definitely getting some evaporative cooling on that one. Okay. So water can exist as a gas, a liquid, or a solid, and that's naturally. I don't know if it's the only one, but it's pretty close. There aren't a whole lot of any kind of things that exist in nature as a solid, liquid, and gas. It might be the only one. You could figure that out and then correct me if you so desire, and that's fine. We value correct and truthful information over anybody's hurt feelings. All right. So water is less dense as a solid than as a liquid because of the hydrogen bonding. It actually spaces out, which is pretty crazy. Is when it's in liquid form, they can be pretty close together, forming hydrogen bonds. But once it becomes an ice cube, they actually kind of sort themselves out in a nice kind of orderly fashion, which makes them sort of less dense and therefore float. You gotta let me know on the doodles. Hopefully they're helpful. All right, so as water freezes, each molecule forms a stable hydrogen bond with its neighbors. As ice crystals form, the molecules are less densely packed than in liquid water. So because ice is less dense, it floats. All right, and this is probably a much better visual on this one, so you can see the ice and you can see it floating. This is kind of a big deal because it actually keeps the water underneath it relatively, so it keeps it liquid. If it were to freeze and not actually float, then we wouldn't have this lovely liquid water underneath to sustain marine life in Arctic environments. Anywho, you can see what happens to these little guys as they kind of space out, is that they'll space themselves out and you get these larger pockets in here. So when you have liquid water, like down here, they'll actually be more densely packed and they'll be moving around, kind of mingling with each other. and they'll do that closer together. So this gives that water that unique property of when it's frozen and in a solid form, it does float on top. Okay, we're at 10 minutes. This is a good place to take a break. So I like to remind everybody to take a break, like maybe a little mental holiday, get a snack, go to the potty, whatever it is that you got to do. Okay, break it out and then come back. All right, so another really important quality of water is that it's our solvent for life. So hopefully remember this from enough kind of science stuff over time, is that a solution is a liquid consisting a uniform mixture of two or more substances. I will say it doesn't always have to be a liquid, but you can get that in chemistry. We're going to talk about liquid solutions in this one. Okay, so we'll talk about liquid ones. So the dissolving agent is the solvent. The substance that is dissolved is the solute. No fancy one for this one. I just think when it's in the larger quantity, which is, usually water, larger amount, it has more letters. So 7 letters here, 6 here. So the larger amount, the thing that's doing the dissolving is the solvent. That's the best I got. If you got better, please share. All right, an aqueous solution is one in which water is the solvent. So aqueous just means it's in water. So you could think of aqua in that terminology. Hope you get the idea. So it's just turning aqua into essentially an adjective. So it's an aqueous, aqueous kind of solution. That's all. Water's versatility as a solvent results from the polarity of its molecules, because it's got those polar molecules due to unequal sharing. And that's because we've unequally shared. Okay, so that results in some positive and kind of negative sections. It makes it a good solvent. So polar or charged solutes dissolve when water molecules surround them, forming aqueous solutions. We can look at table salt as a good example for this. Okay. So table salt has the positive sodium, the negative chlorine, and they kind of form this little crystal together. However, when we put them in water, because water has those positive and negative ends, positive, negatives. So the negatives will always be attracted to the positives of the sodium, and the positives here would be attracted to the chlorine. So that's what's happening, is these little white parts are the hydrogen, and they're all kind of orienting towards the negative of the chlorine. All right, and then the negative parts of the oxygen are all surrounding the positive of the sodium. So the thing about water is that it's really friendly, and if we get a new thing in there that has a charge to it, it really wants to kind of hug and surround and connect with those things. And that's what it does. So it can really dissolve things with charges. All right, in liquid water, a small percentage of water molecules break apart into ions. Sometimes we get hydrogen ions, sometimes we get hydroxide ions. Both of those things are, too reactive for their own good. So a substance that donates hydrogen ions to a solution is called an acid. A base is a substance that reduces the hydrogen ion concentration in a solution. Okay, and it's based on the pH scale. I don't know that we've had a little Easter egg in here yet, so this would be a good time to start one. At least nobody's turned anything in yet, so this would be a great time. So if you want some extra points added on to your quiz next time when I see you, write on a piece of paper. Write me out just a scale, 0 to 14, and then anywhere on there, look up anything, and I'll probably show you some here in a minute that you can use. Find 3 common things and put them on the scale, where they go. Okay? Did you get that one? Did we get the Easter egg here? I call them Easter eggs because you gotta go find them. Okay, but the idea, draw me out the scale, 0 to 14, and then take any items that you want and put them on the scale where they belong. Got it? As far as whether they're acidic or basic, put them on the scale. Done. I'll probably give you 5 points towards your quiz, or 5 percentage points rather. So, might be worth it. So the pH scale is from 0 to 14. Is 0 the most acidic, 14 the most basic? Yeah, there's plenty of good memes about that. You're 11 on the pH scale because you're basic, that kind of thing. That's good. Good to help you remember those. Each pH unit represents a tenfold change in the hydrogen ion concentration in the solution, or the proton concentration in the solution. Good definition: a buffer is a substance that minimizes change in pH. These are actually super important in the human body, just to give you a biological kind of significance. If your pH in your blood changes, you have to have buffers there that say, no, 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 we got to keep it within this range. It's also a part of homeostasis, so it's a good one to know in biology. So a buffer minimizes those changes in pH. It'll accept a hydrogen ion when it's in excess, and then donate it when it's depleted. So it kind of serves this moderator role. All right, we're moving right along. Oh, look at this. Lots of examples that maybe we'll go with a lovely little Easter egg on that one. But you can see closer to the 0 of the scale is battery acid, closer to the basic side, or the most basic we have is oven cleaner, and then somewhere in here is pure water. The fun fact is that blood and your tears are all basic. They are actually slightly basic. Some are around 7.4, so your tears are basic. I'm just kidding. It does make it a fun thing to talk about, though. But again, we can look at, the higher hydrogen ion concentration we find in acidic solutions. We find equal amounts relatively, like 5 hydrogen ions, 5 hydroxide ions, so they're equal. And then we find more OH minus or hydroxide ions in a basic solution. And hopefully, having gone through chemistry, you know that there's some other ways that you can define those things, as far as like Bronsted, Lowry, and some other crap. But you know what? We can stick with hydrogen ions and hydroxides, and we'll be fine with that. We will live. All right. So some scientific thinking, again, connecting it outside to biology for this one, is that we've got some studies that show the effects of rising atmospheric CO2 on coral reefs. So carbon dioxide is the main product from fossil fuel combustion. Fossil fuel combustion is like the gasoline combustion that goes on in cars. Okay, even, I can't survive without my car, and so I'm a contributor to this, even though, what can we do right now? Okay. But increasing the carbon dioxide, the increase is happening in the atmosphere because of this. And it's linked to global climate change. So it's contributing to some change in the climate, some weird stuff happening. Okay. About 25% of the human-generated CO2 is absorbed by the oceans. And CO2 dissolved in salt water actually lowers the pH of the ocean in a process called ocean acidification. You could think about this because actually when you have a soda, like let's say you have a Coke and it's got the little CO2 bubbles in it, think about those things are usually acidic. So like a Coke is definitely an acid. It's got that acid to it. So when we add some sort of CO2 bubbles to the ocean, we're making it more like Coke or, seltzer water or ginger ale type. We're lowering the pH of it. So as seawater acidifies, we have extra hydrogen ions that combine with these crazy things of carbonate ions and form bicarbonate ions, more and more stuff. So the reaction reduces the carbonate ion concentration that are available to corals and other shell-building animals. So now we've got some other animals that we wouldn't think of necessarily that are being affected by this. All right. So in a controlled experiment, they did look at the effect of decreasing carbonate ion concentration for calcium deposition of reef organisms. So the lowered concentration of carbonate ions, the lower the rate of calcification, or being able to use calcium to like harden or for like shells. Okay, so the result of the experiment and observational field studies of sites where pH naturally varies have dire implications for the health of coral reefs and the diversity of the organisms they support. So if you look at it, let's see, calcification rate, if we increase the amount of calcification that's going on, and we have an increased, well, here we go, we have an increase in these carbonate ions, we'll see an increase in calcification. So those two things are directly related to each other. So more CO2 bubbles, more the pH is lowered. All right, so an emergent property, one of those things that emerges that makes it different of water support life on Earth. So when astrobiologists search for signs of extraterrestrial life on distant planets, they're looking for water. You've probably heard of that when it comes to NASA and their studies on Mars. They're looking for evidence of water and water molecules because it just can do that. All right, and so that ends it. So turns out it wasn't a very long lecture this time, which is good. I would, if you haven't, and some of that doesn't entirely make sense, do look back at the hydrogen bond stuff. We'll talk about it some more, but use this time to look at hydrogen bonds, see how it relates to water and all these properties, and we will quiz over it first thing when we're in class next time, and then we'll do lots of activities to make sure that we get this one. As always, if you have any questions at all or not understanding it or just anything, shoot me an email at my Gmail account and I'd be happy to get back to you and let you know. All right. Have a good one.